Thank you for being here on Saturday afternoon. Only for the cake, yes. So I will thank those of you that will stay after the cake. Those will be the real heroes. You are just okay. So let me start by acknowledging the references that I forgot to do yesterday. Of course, I'm talking about Hawking radiation, so I don't need to quote all original Hawking paper. Because you already know him. And there are several papers that will be in the notes, not in the version that I will send to you next week, but I will add I try to add all of them. But there are also several nice books. Uh, One of them that actually is I will kind of follow today is Birrell and Davis, Quantum Filtering Cool Spacetime, which is a very nice book. It's a classic. But also another one that I used for the lecture of yesterday was Fabri Navarro Salas Modeling Black Hole Evaporation, which is a newer book, but also a very nice one. And there are many others, but these are the two main ones I've used in preparing the lectures. Okay. Um, let's start by repeating the results we obtained yesterday. Yesterday we looked at black holes that form via gravitational collapse. So was the Penrose diagram that I drew. I don't know how many times. And we have seen that because of, in this specific case, if we consider yesterday, the dynamics of the null shell collapsing. So because of we have a dynamical spacetime, we can have Hawking radiation. So we have particle production from the black hole. So we compared the vacuum states here on Scri minus with what an observer will see on Scri plus. And we've seen that if we prepare a vacuum state on Scri minus, an observer on Scri plus will measure particles. Today we want to discuss, and also because this will allow us to answer questions also about this case, but today we want to discuss what happens for the eternal black hole spacetimes. Because yesterday I said a strong statement, which is that eternal black holes do not emit radiation, do not evaporate. But of course, there are other ways that you may be aware of to compute Hawking radiation that they use the static geometry, for instance, the path integral formulation, and you do get some radiation, and we need to understand how is that possible. And in doing so, we will also uh, introduce there's some tools that will teach us again stuff about this spacetime here, which for me this is the physically interesting one, but of course there are people that work with this one. So how is it possible that we can have some particles in this spacetime? So as I mentioned yesterday, if there is a unique time-like Killing vector, which is in this case it exists, I can split the modes into the frequency mode into positive and negative frequency in a unique way. And this will not generate particle production, basically because the Bogoliubov coefficient beta will be 0. So here there is a preferred time associated with the Killing vector, which is t. So I can split the modes with the positive and negative frequency associated with this time t. And how these modes will look like, right? So we have right-going or outgoing observers, which are modes of constant t minus r star equal constant, which is basically modes of constant u, like we discussed yesterday. And then the other ones, the left-going modes, v t plus r star equal constant. And so you can have this set of modes like by, let's say, like right going. Let's forget about the normalization factor for now. Well, no, let's write the normalization factor. 8 by omega. And then we have e to the minus I omega u, and left equal 1 over 8 pi omega e to the minus I omega b. And this you can do, I mean, in the future, in the past, whenever. And if you just do what we done yesterday, which was tracing modes from square plus back to square minus. I mean, here, square minus, you don't longer have a basis of modes, right? Because remember, on square minus, we had the left-going modes, and then you have reflection. And so the left-going and left-going, outgoing modes are not independent because they are the same, just reflected along, just reflected across r equals 0. But here, so you need to do both the right-going and the left-going modes. And if you just reflect them in a point in the future, in which you have e to the minus I omega, for instance, the right-going modes, and you place it back, it does not change, right? So the modes in the future is e to the minus I omega, in the past, e to the minus I omega. And the left-going modes is the same, right? They don't change at all. So the Bogoliubov coefficient that Ravan asked me to compute are trivial because it's just alpha is the identity matrix and beta is 0, right? But we also see something that is non-trivial from what I discussed in the first lecture yesterday about the coordinates on this spacetime, is that this e to the minus I omega u and e to the minus I omega v, which are the correct modes on square minus and square plus, are not good modes at the horizons. So neither of them, because u and v diverges at the horizon, right? So in particular, u diverges here and v diverges here. And so this is at the base of the fact that there is going to be radiation, but it's not, we will see, it's not particle production from black holes. So what is it going to be? This is something that we are going to understand today. In order to understand it, we will need to introduce some semi-classical stress energy tensor, which also Ravan mentioned in his T-menu, in his lectures. And basically, the semi-classical stress energy tensor is something you can introduce to when you can keep treating the gravitational field as a classical field, but you want to consider effects of quantum matter. So the Einstein equations, d mu is equal to 8 pi g. I keep reminding g. I'm making a good job. D mu classical. And in cases where you are still able to treat this classically, but you might want to consider some quantum effects, you can add the expectation values of d mu in some quantum fields in some specific vacuum states. And of course, the choices of vacuum states are going to be important. Right? But this is not the full theory of quantum gravity, it's just semi-classical gravity. And this is very useful for several scenarios. And in particular, it's the first thing you want to do when you want to start to consider back reaction. Because we didn't do that yesterday, and actually we will not really do it now. But if you want to start to consider back reaction, you can add this Einstein equation. Yesterday, we just considered a free scalar field on a fixed, not fixed, a dynamical background, but we didn't look at what is the scalar field going to do, how is the scalar field going to affect the background. This is something you can add to obtain the first terms to that. And we will actually mention something at the end of the lecture. But the main reason we are going to introduce this object today is because studying this object is telling us about some information about the scalar field, right? Okay, now doing that is actually extremely. I mean, there are a lot of challenges that are hidden when we want to do that. And the main one I would say you can imagine is the fact that you're going to have divergences because when you You can compute this classical stress energy tensor and then promote the fields into quantum fields, but then this will lead to divergences. So we need to understand how to renormalize the result, which is highly non-trivial. Um, a situation in which this uh, easier, not easy, but easier, and it can be done analytically, are when we restrict to 2 dimensions. And so this is actually, we are going to do it now. We're not going to do all the computation, but I will tell you uh, why this is actually doable and why we can still learn something out of it. So we restrict for the moment to 2-dimensional black holes. And as Ivano said during his lecture, gravity in 2D is boring. I mean, I agree. So the only reason why I do this restriction to 2D is because I still can learn something out of it for 4-dimensional black holes. And in particular, if you, it's a first approximation to compute the stress energy tensor in spherically symmetric spacetimes. So if you do the what's called the sorry, one. Mhm. Yeah, you mean the trace anomaly? Yeah. No, there's not I mean, the problem is not that the trace anomaly is different. Of course, the trace anomaly will play a role, but it's actually, I mean, I can just anticipate it now, but the reason why in 2D it's easier is that every 2D space-time is conformally flat. Yeah? Hmm? Look, yeah. So you can just, yeah, I'm not worried about global effects, but yeah, locally. So this is actually what is helping you to do this. Mhm. Yeah, I don't know. I don't know if this was done and helped lead to uh, something which is giving some extra information with respect to this. But yeah, of course, in 4D, it's not like you cannot do anything, but analytical results are just in 2D. So I'm just going to use analytical results, right? So I mean, there are some analytical results in 4D, but not a full form for a generic spacetime of the stress energy tensor. And there is so what I was saying is that this is a first approximation. So if you just do the standard expansion in spherical harmonics and you only restrict to L equals 0 mode, so to S wave, you can relate the non-angular components of the 4-dimensional stress energy tensor. So A and B indicates the 2 indices that are not angular with the 2-dimensional stress energy tensor this way. This is actually a simple computation. You will find it in the notes. And of course, this approximation will break down. For sure, it will break down at r equals 0, for instance, because we have 1 over r squared here. But anyway, at r equals 0, we don't expect semi-classical gravity to be a good description. We want a full theory of quantum gravity. So we don't care about the fact that the approximation will break down there. So, but it can give us some information at the horizon scale, and also there are some results in a 4-dimensional with the aid of some numerical parts that kind of confirm what you get. Yeah? And as I was mentioning, so this is why it's interesting because you can kind of reduce to you can get some information also for this space-time. And so as I was mentioning to Ravan, why is it easier is because of the information on the expectation value of the energy tensor can be recovered purely by the trace anomaly. Um, so if you have a conformally invariant action, you get classically that the stress energy tensor is stressless. That the energy tensor defined as 2 square root of minus g mu nu. If the action is conformal invariant, then you get that t mu mu is 0 classically. At the quantum level, this is no longer true because of because the name of conformal anomaly, and this the renormalization procedure um, that spoils this effect. But the point is that the quantum level, the trace can be calculated with easier than the how is the full stress energy tensor. And if you have any question how to compute this trace, ask this Ivano, for instance, that he knows much better than me. But anyway, this is a constant that can be evaluated. I don't remember now the value, 1 over 25 pi, I think, I don't know. And this is the Ricci scalar. And in 4 dimension, you have other terms, but it will be at this stage it will be not particularly different. Um, but now the real difference is that in 2D you can always write the metric in this way, some conformal factor. Let's call it omega. No, yeah. Well, C. C is fine. Let's see C omega mu nu. Okay. And so given that, so if you consider something that an action that is conformally invariant and the geometry that is conformally flat, the problem some places called conformally trivial. It's not conformally trivial, but conformally you can reduce to the computation of that you will do in flat spacetime. And the only terms extra that appears is some terms that can be evaluated via the knowledge of the trace anomaly. Right? So in this way, you can understand the quantum effects because they are here. Sorry, the quantum the curved space-time effects will be in here, and then the other effects will be something that you evaluate in flat space-time. Yeah. Yeah. Mm-hmm. What do you mean? Mm, like I mean, I don't know. Probably no. I mean, the other team will still be valid. I think you have a Lagrange, you have a symmetry. This gives to conserve charges. Yeah, I don't see. I mean, to me, what I know, no. Um, okay, I will not do the full computation because it's very long. Also, I'm not an expert on that. But just to give you a few steps. The idea is to define an effective action W that is related to the quantum stress energy tensor in the same way that is that the classical action related to the classical stress energy tensor. So you have delta G mu nu, well, -2 over G is equal to T mu nu. And the difficulty will be in the study of this effective action. And then once you do that, if you strict with the conformal invariant matter, then you can perform a transformation that brings you the metric in flat Minkowski spacetime. Yeah, and so this is the first time is to define this. Then you do this transformation here, and you see how it acts on W, and so you get W of the original geometry G is equal to W in the new geometry background, which is the flat spacetime. And then plus you have, so this is just the variation of the effective action. This is related to the stress energy tensor. T, but the variation of something which is just conformal. So this is just related to this to the trace of the stress energy tensor. So it will give you something. The mm, well, at this moment we can this say 2x because we are fixed in 2 dimension, square root of minus g, and then you have the trace of the effective um, of the energy momentum tensor, and then you have the variation of so delta g, but this delta g is just this conformal factor c, right? And so when you do that, now the problem of renormalization and the variation and defining everything is split in something that you can compute, because we can compute the stress of the stress energy tensor, just the conformal anomaly, and something which depends on flat spacetime. So the fact, so this is just the motivation of why this is simpler and why you generally get two contribution. One which and also let me know that this anomaly here, I didn't write down the quantum states that we are computing, so this term will be independent from that, and the choice of the quantum states will affect this first contribution here. Yeah. No. Okay. Well, perfect. Okay, as I said, I'm not going to do the computation, but let me write down the results, and then we will study this result, and we will see what is teaching us. And if you're interested, this is to the computation is chapter 6 of Will and Davis. It's something that at some point everyone will study. Everyone that study work on quantum field theory and core space time. I think it's. It's something to read, but it's I mean, it's not an easy read, but it's something you should spend some time on doing. And yeah, so I'll write down the result here. So expectation value in some given state that I've not specified yet, D, this with our metric, spacetime metric, is going to be equal to the 1 over square root of minus g. It's not particularly relevant, but the results that you would obtain doing the computation in flat spacetime on the same quantum state. So the information on the quantum state will be here, plus the term that you obtain coming from here, which you can compute and is given by this quantity. And now I'm going to explain what they are. So this is just the Ricci scalar. This is the metric, and this theta mu nu is we can fix now some coordinates, and if you use this is the metric, and if you go to the UV coordinate that we defined and we worked a lot these days, these are the components: -1 over 12 c to the 1/2 du square c to the -1/2 theta bv is the same, but the derivative is the derivative with respect to v. And then you have the non-diagonal terms are actually 0. Okay. So here you just need to trust me, or better trust the book. But of course, if in the future you're going to work on this problem, then you will need to actually check this computation. Otherwise, we are going to learn a lot from this result. Okay, before actually applying this result and see what we can learn out of it, what we can do is to ask the question, when is a stress energy tensor regular, right? So when divergences are bad and when it is regular. And a simple criteria is that stress energy tensor is a good stress energy tensor when its components are finite in a coordinate base which is well behaved everywhere, right? We brought here the result in this small UMV, so I did some fixed coordinates that, as I mentioned, they are divergent in part of the horizons, right? In the diagram you've seen there. So these are not necessarily the good coordinates to understand if the result is going to be divergent or not. So we need to go to the Kruskal coordinates. And going to the Kruskal coordinates, I mean, it's just a change of coordinates because this is a tensorial quantity. So yeah, mu nu in some coordinates x is just uh, yeah, this is the standard tensorial transformation, right? In the coordinate, yeah, from x bar to x. We just want to go to from capital U to small u, from the Kruskal to the unit of Wittgenstein coordinates. And so you just need to do this. And you remember that the Kruskal coordinate are just the exponential of the edit of Wittgenstein one. So the derivative is just u. And so what you get is, let me write it here, that E u, u is equal to uh, by kappa square, which is the surface gravity, 1 over 4m kappa. Uh, u, okay. And similar for V. Sorry, this is u square or u to the minus 2, u square, right? Similar for V. And then the mx coordinates are E, u, V. And then you have u times V. Okay. Uh, so what are now the, given these relations, what are the conditions on this energy tensor with UU, VV, and UV coordinates that we need to impose in order to have something which is well behaved? I know that we could just do the computation in the Kruskal coordinates, but this is, I mean, usually the results are within these coordinates, and yeah, we can stick with that. Uh, Okay, the surface gravity. It's a constant anyway, it's not particularly relevant. Um, I mean, yeah, there is the interpretation. I think it's easier to read without using the Kruskal coordinates, but so it's useful to do this step. Remember that this side of this part of the horizon, all of it, so h plus right, and also h left minus. But let's focus on this part of the space time. Let's not worry about the parallel universe. Let's say we had capital U was equal to 0. And in this other part, we had capital V equal to 0. Okay. So if we want something which is from this relation, if we want something And also something else that was not how it was equal to 0. This was proportional to 1 minus 2m over r. This is something we discussed yesterday. And again here, this was proportional to 1 minus 2m over r. Okay, so when r goes to rs, this is 0. So if you want something which is regular, uh, regularity on H plus, for instance, right? We want this U, this one, and this one to be finite, and this is multiplied by something which goes to 0 as well as this. So in order to have something which is regular, we need that 1 minus 2 gm over r squared times u. It's, let's say, less than infinity. Let me write this, which means that this is finite to the minus 2, sorry. Because I just taking u to the minus 2 there. Similarly, for the TUV, this is just to the minus 1. And again, we want this to be finite. And finally, the VV component just need to be finite. Does not need to vanish quadratically or linearly. This is on HR, where capital U is equal to 0 and capital V is finite. And now we want the same, but on H minus. So the past horizon, the one which we can argue it's unphysical because it's not present in this one, but it's still useful to understand the regularity condition. And you can see it's basically the same. It's just that now V is the one which is going to diverge and U is the one that is going to be finite. So we have basically the very similar condition. U just need to be finite. Then T U V multiplied by this divergent factor needs to be finite. And then this one to the minus 2 T V V must be finite. I hope that my handwriting is sufficiently clear that you can distinguish U and V, but just ask if you are confused by U and V, because yeah, my handwriting is not the best, so they could be mixed. But these are just the conditions that we need. And now that we have all the conditions, what we are going to do is just to express this result. Of course, I need to tell you how to evaluate this term. Again, I'm giving you the result. In several important states, and study what are the properties in these states. So let me check some. Yeah, I was checking how to spell the word boulevard for boulevard state, which is the first one that we consider. Yeah. So we are now considering different choices of vacuum. I will tell you how these vacuum are defined. I will write down the result. And we are studying the properties in this vacuum. And this will teach us all the questions that I asked yesterday. Yeah, I checked how to spell boulevard and I forget in the meantime. So, hoping that there is no typo in my notes. This is how you're supposed to spell it. So boulevard state. How is this state defined? This is the state that we have naively introduced before. This the one that you get using splitting the modes using the time like Killing vector, and is the state that is a vacuum bottom square minus and square plus. So this state, uh, let's call it B or boulevard. It's defined by splitting the modes in this way. Again, we'll give the sum of omega. Well, you can actually we could write the integral here, but anyway, 4 pi. Omega. Oh yeah, let's write integral. At this stage, we don't really need to do the. mm, I mean, we can consider the plane waves here. We don't need to do the wave packets as we did yesterday to obtain final results. E to the minus I omega v, and then we can a omega, and now we need to add like left because these are the left going modes, and then we have again the right going modes. 8 pi omega e to the minus I omega u a omega, right? And then you have the emission conjugate. So this is similar to the state that we defined yesterday, but yesterday we only had the left going modes, and then the right one were the reflection across R equals 0. And now we need, in order to have a base, we need both quantities. If we now rewrite that result in for the Boulevard state, this is a special state in which the term that you will get in if you're doing the computation in Minkowski spacetime vanishes, because this is the state which is corresponds to the vacuum state in Minkowski spacetime, and it's also why the state we start an analysis with. So if we write the result, just compute this theta, the Ricci scalar. What you get is the following. Yeah. E u nu equal to minus 1 over 192 pi f prime of sorry, I called it C prime over G mu nu is equal to C U and V eta mu nu. So this C is 1 minus 2m over R, right? 2gm over R. And of course, R here is we should read it as a function of U and V, and then do this. Just plug the result, just plug that result and do some basic algebra. This is what you get. C prime square minus 2 C over C second over. This is the TUU component. And this is also equal to the EVV component. And the UV component is equal to 1 over 96 pi F F second. Again, yeah. I don't know why I used C today because it was the conformal factor. Sometimes it's called C, but usually we call F anyway. Okay. So now we ask, is this state, so what are the properties of this state? And actually it's also useful to um, just compute the derivatives and so on. And you get the result is 1 over 24 pi minus m g over r cube plus 3 half g square m square over r to the fourth. And this one here is minus 1 over 24 pi 1 minus 2m g over r and g over r cube. Okay, so now let's see. First of all, we built this state with the expectation that this state was going. Yes, thank you. So we built this state with the expectation that it was going to be vacuum asymptotica, and it was going to be vacuum both at Cray minus and at Cray plus. This was the state that we were discussing before. It cannot have any particle production because this way of splitting, the one given by the Killing vector, is not going to produce any state. So is this true? Yes, this is true. Because you see that all the terms vanish at r going to infinity. So Scray plus and Scray minus, this state is empty. It's a vacuum state for observer living on Scray minus and Scray plus. Right? But then we ask, okay, what about the regularity conditions? Are the regularity conditions met on this state? And we need to check them both on H plus, the future black hole horizon, and H minus, the past white hole horizon. And okay, let's start from the TUV, which is the same in both cases. And this is fine, yeah. Yeah, it can be. Yeah, we will, it's just locally negative stress energy tensor. Like it's, I mean, in principle, it's possible, right? It's, I mean, globally, I mean, the Milton is bounded, but locally you can have negative so in fact, the semi-classical physics violates the standard null energy condition. Not all of them, but they violate some of them. And this is something that I mean, it's just something that happens. There is no fundamental physical law that predicts it. Just we expect standard classical matter to satisfy the energy condition because this is based on the experience, right? This is what we saw, and this is what we expect from a standard classical matter, right? But when we quantize quantum field, then you can have something which is what is hmm yeah, yeah, yeah. Okay, the important point is that it is going to vanish asymptotically, and it does. But yeah, yeah. I mean, but I cannot really define a particle final distance. So it's not a particle with negative energy, right? It's just negative, yeah, violation of energy condition, and is, I mean, allowed by the theory, and this is what you get in this state for uh, uh, for this computation. And actually, I mean, there are bigger problems. I would say that is what I was saying now. Is that yes, this quantity here vanishes at the horizon, right? So this does not give any problem. But this quantity here, TUU and TVV, they are both finite at the horizon. And in particular, the finiteness of TUU at the horizon, so does not vanish. It's a problem for the regularity on the future black hole horizon, H plus, that is divergent. You have regular observer, like free falling observer, to measure infinities, right? And the same is true due to the divergence of this state here on the side H minus. Also on H minus, you have something which is divergent, right? So this state is not a, a good quantum state for a black hole, but on the other hand, this is the state we will expect from a static matter configuration without horizon space. So we will expect this state to be the state describing the quantum field, the vacuum, the quantum field outside a star, compact object that does not have an horizon, because we will expect that without the horizon you do not create particles. So if you start with vacuum, you will have vacuum also asymptotically. But this evidently is not possible here. Mhm.
Now try to do perturbations. This
But I mean, also the first thing, yeah, I don't know.
so
Yeah, yeah, yeah. No. I mean, I don't know, but this is, I mean, as I said, this is not even the zero step. We have not plugged it into the Einstein equation. Then you should solve the system consistently. But yeah, I mean, if you want, for instance, to avoid horizon formation and this kind of stuff, then you need violation of energy condition. If you want to avoid singularities, you need to avoid the violation of energy condition. So, I mean, this is just a fact. Is that I will not even neither call it I mean, it's not an inconsistency at this stage. It's just this is what happened. Now we need to be aware of this because this is not exotic physics. Yeah, yeah, yeah. Yeah, no, I mean, me neither. But yeah, this is yeah.
Asymptotically we do have the detector or detector, so we have like
Mhm.
for concept with the argument to go through. So what
I have not seen the computation in asymptotically de Sitter or quantum de Sitter or anti de Sitter. Let me think if I remember something. Let's discuss later because I need to think about it. I'm not sure. Yeah. Okay. Any other questions? No? Okay, so this is not a good quantum state. So how do we define a better one? To define a different state means defining a different way of doing the splitting. So finding the new coordinates v and u. Right? So the simplest thing you can do is to have a new coordinate v tilde, which is just v tilde of v, and u tilde, which is just u tilde of u. Mhm. And this will change this term here. And the way it will change, I will just I will give you the result once again. I mean, this computation in this lecture, I'm not doing many computations. Some of them because they are trivial, just plug this in, and some other because they are extremely long. So if you do that, if you do this change, wait, sorry, I wanted to let's be precise here. So this is the Boulevard vacuum. And I will try to keep track of the vacuum from now on because before I was saying stuff which were true regardless of the choice of the vacuum, but now what I'm going to obtain will depend on the choice of the vacuum. So this means that I mean you're changing the splitting into phi is equal to the integral of pi omega, and then you have e to the minus I omega v tilde a omega plus e to the minus I omega u tilde. Right? This is not a change of coordinates. This is a change of choice in the vacuum. Okay? So,
Is it not a change of
I mean, you can see as a change of coordinates of the observer that you choose. Right? But I'm going to still write, I can still write the results in these coordinates here. So this is going to, this is the change of the difference of how you do the splitting, positive and negative frequency modes. But I don't need to, I mean, I can describe this in any coordinates. And this is, I'm choosing a specific observer. Observer solid, in this case, observer solidal with with V and U, and here U tilde and V tilde, and then we will make some choices, right? So the point is that you cannot obtain, let's call it 0 tilde, the stress energy tensor, in this new coordinate. This is not just going to be equal to the way the tensor transform with starting from the Boolean vacuum. This is going to be like there are some extra steps more involved. And I'm guaranteeing now the result. The TUU component in this new vacuum, you can write it down. It's going to be the value that you obtain in the Boolean vacuum, which is basically only these geometrical terms, right? And then you have something extra, which we denotes in this way -1 over 24 pi u tilde u. This denotes the Schwarzschild derivatives, which is defined in this way. Let me define it here in the bottom. F of x is defined as the third derivative divided by the first derivative minus 3 over 2 f prime of x. Okay. Fine. Just trust me for now. If you ever want to work on this, do the computation.
the quality of the vacuum?
Yeah. So I am basically giving you the results of this generic expression in a different vacuum. The Boolean vacuum is the one we started with, and is kind of special because it's the one in which this term does not enter, this one, and you only have the terms that are due to geometrical quantities, so the terms that it does not correspond to any particles in the flat spacetime, but you have some geometrical quantities. And this is something that has to do with how you do the normalization of the vacuum states and how you do the computation in the Minkowski. So the same state, but computed in Minkowski spacetime. And this is something that you can compute, but I didn't do it. And this is the result, where this symbol here means this expression. Right? So it's the Schwarzschild derivative of the first quantity with respect to the second. U tilde is a function of u. Okay, and the same is true also for the VV component. Minus 24 pi p tilde V. Whereas the mixed component does not change, and does not change because I choose V tilde only as a function of V and U tilde only as a function of U. Otherwise, also the mixed term will change. VU is equal to VU. Okay. So this is an important result that I'm just stating. Again, sorry if today is mostly stating results, but this is, I mean, I think this is important because this is teaching us a lot, but we don't have time to to go through the derivations. Yeah. Yes, everything should be. Yeah. Oh, you are very good. Wow. Okay. Yeah. Well, now it's minus plus because it's two dimension. But time is minus. Yeah. Time is minus and space is plus. Okay, so this was the kind of heavy part. Now we can discuss some physical intuition. So we've seen something that was divergence of both H minus and H plus, defining the state in this way, right? Now I said let's do some change of observer to try to find states that are better behaved. So if I ask you a question to find the observer that let's not care for the moment about H minus, but they give you a state which is well behaved on H plus. Do you have any guess which type of transformation I need to do to have some state which is well behaved on H plus? Let's not care for the moment on H minus. And I repeat that on H minus, so this term, the non-diagonal one, was fine all the time. And this is good because this transformation does not change it. And these were the regularity condition, right? So basically TU was the problem. So you need to change the U coordinate with something else and find a state which is regular. So are there any guess of how to find a good state, changing the U coordinate to get something which is regular at the horizon? Any random guess? Yes. So what I do here is choose Kruskal coordinate U. And so the choice, the way I will split the vacuum is I'm not going to change this. And here I choose the Kruskal coordinates. Yeah. Yes, no, the question is, yes, yeah, I'm going to read. The question is, this result are for a scalar field. How do I change it if I have a fermionic field? And then the one answer, that sounds painful. And that is exactly my answer. That is painful. I mean, you can do it. It's just painful. But uh, of course, yeah. I mean, you should have I mean, I actually have not seen the computation for the fermionic field, but I'm sure that you can do it. It's just more difficult, and mostly the difficulty will come from this term here. But yeah, of course, you should do it for a scalar field. You should do for a vector field. You should do for all the fields. But conceptually, this I think has the points that matter. So I can delete here because we have already written the regularity conditions. And yeah, I think now I can also delete this. Okay, it's good. I could like, yes, I thought someone has done it. Well, I don't have it now, but yeah, I can look for it later. But I'm actually not sure if it's been. I think it's been done, but we can look for it. But I don't know now. I have not started this. Yeah, all the time. Okay, these we're going to keep because these are the regularity condition. And so, so we have a suggestion to change U into the Kruskal coordinate. And this is actually the definition of the Unruh state. So let me write it again. Pi e omega 8 pi omega, and yeah, e to the minus I omega v a omega left plus e to the minus I omega capital U a omega right plus Hermitian conjugates. And now what we have from these equations here. So first of all, the let's call it Uru. This U stands for Uru. Now the V U component, as I said, is never going to change because we are already doing that the transformation here. So it's the same as in Boulevard. Then in this case, also the VV component does not change. No. But the U component is going to change. So you are going to be the Boulevard term plus TUU. Plus, so TUU plus this term here. And plus or minus 1 over 24 by U. Oh. Okay. And now remember that we defined the Kruskal coordinate as 2v minus e to the kappa u. So this is quite simple to evaluate this the derivative because it's just exponential and derivative of exponential. So you just get k square with some k square with some numerical factor, and you can check if you compute also the numerical factor, right? Because this is just k square when you divide by f prime, and that one as well, and then you get a numerical factor. So u is equal to k square. The numerical factor is 1/2. So minus one is minus 1/2. So minus 1 over 24 pi give you just 48 pi. And this k is reminder is 1 over 4 mg. Okay. And now let's just do this. Let's just do that. And if we do that, we just have the value that we had written over there plus this constant. Just do the sum, whatever, and you get. If you want to do it, double check the numerical factors because they might be wrong. In the notes that I will send you, I will double check them. But aside from numerical factor, the important terms are this one. I mean, all the terms are this beside numerical factor. 1 plus g m plus 12 g squared m squared or r squared. Okay, amazing. Now we have something which is which has the right prefactor, so it vanishes at the horizon. It vanishes quadratically, and so this state is well behaved on H plus, right? 25 minutes. That's exactly the point. It does not vanish anymore at r equal to infinity. And in fact, and the point is that because we have added this term, right? This term is a constant term. We added it. So I will just rewrite it here, so I don't need to copy everything. Plus k square over 48 pi. Okay. So what we've done was to add some terms, which at infinity is a constant. So it's a regular flux at infinity, and at the horizon does not vanish. So this term at the horizon leads to something which is divergent, but is exactly divergent in a way to cancel the divergence coming here, which is beautiful if you think about it, right? It's a kind of a magic cancellation because this term, we computed them coming from very different places, right? This was something which was just the geometry of the space-time, and this is something that we computed using the trace anomaly, and this was something that was due to the specific state that was done, the computation done with the basically the Minkowski flat metric. And the fact that you have this amazing cancellation is not an accident. It's because we are now considering observer which has well behaved at the horizon, but it's very nice, right? We are deleting. We have terms that that cancel each other and give you something which is finite. It's kind of a way of handling the divergences, but this is actually coming from. It's finite. Yeah. So this is finite in these coordinates that are not well behaved at infinity. So when you go back and you transform it to Kruskal coordinates, you get something which is divergent, right? So it's and also this term, right? This is finite, but then at the horizon, it's going to be giving you something which is divergent, and a divergent flux at the horizon, which is canceling the divergent flux there. And now if we draw, let's only focus on this region here. I mean, the component TU means that there is a flux of energy in the U direction. And of course, I mean, the precise form is something, but this is something which is finite at the horizon once you because it goes to zero quadratic, but once you transform on coordinates that are regular at the horizon, this gives you a finite contribution. And it's something that you also have on Scray plus. So you have a flux of outgoing energy on Scray plus. Right? And what is this? And this is vacuum on Scray minus. And actually, you can check. We will see later that this is a thermal state on. This is the same that you will get if you have a thermal state on Scray plus, right? So is this Hawking radiation? I mean, this is Hawking radiation, but this is the evaporation of black holes that I was telling you before. You don't have for eternal geometries. Well, this is not really coming from the production of the black hole and the splitting as we did before. This is coming from H minus because their state is still divergent here. So here we still have something divergent, and this is creating this flux over here. Okay? So if you continue this flux, and it's everywhere, right? It's also every time. So this is not creation because we are creating a black hole, a dynamical field, and so on. This is something that we still have a divergent state here, and but Scray plus is something which emits radiation. And of course, we can do the same and define a state which is regular everywhere, which is the Hartley Hawking state. H. And now, do you know how to do that? Like you answered correctly before. So how do we choose our server to have something which is now also regular on H minus? Exactly. So we also take the Kruskal coordinate for V, and what we get is, of course, I mean, the relation Kruskal coordinate is exactly the same, U and V. We get exactly the same for that we obtained before, but now also for the VV component. So what we will get, I will not do it because it's exactly the same. We get that in the Hartley-Hawking state, the EVU, the mixed one, never change, and it's still equal to the one in the Boulevard state, and it's equal to the one in the Uru state. Now the TUU in the Hartley-Hawking state is now given that we I mean, we use both Kruskal coordinates now. We use capital V and capital U. It's the same that we had before in the Unruh state. So it's let me rewrite it. Boulevard in TUU plus k square over 48 pi. And now the same here. TVV in the Boulevard state plus k square over 48 pi. Okay. And so the actually is exactly the same expression of here. So we can do exactly the same consideration as before. Now we have one state which is regular everywhere. This state is going to be regular on H plus, regular on H minus. So it's perfectly regular everywhere. It's going to have radiation on square plus, but it also has radiation on square minus. So you have outgoing flux of radiation on square minus. And then in the middle for finite R, you have something complicated, and then you have something regular on both horizons. And this radiation, which is originated on square minus, is the one that you need to have. I mean, it's going to give you a finite state everywhere, and the radiation on H plus. So this is what I meant yesterday by saying that eternal black holes do not emit evaporation. Eternal black holes lives inside a thermal bath. So they are in equilibrium with the ingoing and outgoing flux of radiation. They are not producing particles because the metric is static. Static. But there is something here, which is actually basically just a Nuru effect. For those of you that are familiar with that, it's just that the observer that are well behaved at the horizons, and the observer are at the square plus are not the same observer. They are accelerating with respect to each other. So if you choose the state, which is well behaved on the horizon, and actually you can do the same analysis also well behaved here, then you have flux of radiations, both incoming from past infinity and outgoing to future infinity. Okay, now we have something which is 15 minutes. We found the main vacuum states. We've described them, and I hope that this this was useful. Yeah.
How can I get finite
Yeah.
on the horizon that also vanishes?
No, this you cannot get. This you cannot get. You can have the different states, but then there will be non-static expectation values. You can do something crazier, but these are the the main one. If you want something which is static, it is what you want because the background geometry is static, so you will not put something which is the time dependence. And no, you will never get something which is regular everywhere and the vacuum here and here. Huh? Yes, I think it can be proved. Yes. This is and this is the core of the result. So you can put something which is regular everywhere, but the price you have to pay is that you cannot have something which is vacuum in the asymptotic regions. Okay. So this is about the static black holes, but I also said yesterday that we were going also to learn something about the black holes that form via gravitational collapse with this method. And the reason why we can do that is that we can actually we can also do this something similar to this for let me delete somewhere. So the last state that I want to consider I want to leave this here is the in state. Right? So the in state is the state that we were considering yesterday. Is actually we defined only for the collapsing geometries, not here. But I want to see what happens if I put these modes in on this spacetime and I do this analysis here. So the way I split the modes in state. Yeah. Yes. Of course, this will give something that will not really make sense everywhere. Will make sense only in some region. But this is still teaching us something. The omega. E to the minus I omega v. Remember that we had this e to the minus I omega v yesterday. That's the state on Scray minus. Right? And then on the right going state, what did we choose? We choose the state that are reflecting our plus, which were plus e to the minus I omega u in. Remember that yesterday we had this state here. And now we could do some, I mean, the same, with a similar analysis here, but now u in depends on both u and v in. So actually we cannot really use this formula. We will have something different. But the main point is we want to understand what happened asymptotically. And if you look at the way u in and u out. So now u out is the u in the Schwarzschild geometry. So it's this u used before many times. I don't know. This u here. This is what yesterday we called u out. The way they were related, if we look at the some intermediate result we obtained yesterday, was u out, which now is just u. We call it u today. I didn't think as a coordinate in the Schwarzschild space-time. We obtain it was equal to u in minus 4gm logarithm of of vh, v of the horizon, minus u in or some constant for gm. Okay. And now if we look at what happened at late time, so close to the horizon, so u in close to vh, late time, you get that the relation between u and u in is aside from a multiplicative constant is basically the same relation between editor fields and a u and Kruskal u. Yeah, you just okay, late times this is irrelevant because it's a constant, and then you just exponentiate. Remember, 4 over gm is the surface gravity, and this will give you just a multiplicative irrelevant constant. Right? So late time, late u in for late times here, this region here. So some late time region, which is the one we are actually interested in. U in is proportional to u. Right? So at late time, the in state has exactly the same property of the Uru state because we choose v and u in coordinate, which at late time reduces to the Kruskal state. Right? And so this is why the Uru state is actually particularly relevant because the Uru state is divergent on H minus, but we don't care if we are considering the collapsing geometry because on H minus is not part of the manifold. And a late time here that does not include square minus, you have the in state and u state are the same. So in particular, at late time, you get exactly the same flux of radiation. Right? And also, I mean, given that we know that the Uru state, the in state, this radiation is due to the thermal radiation, we can also understand from here that this is given the thermal spectrum. We cannot compute the correlation from here, but we know that this is basically the radiation. It corresponds to a thermal emission. Okay. How much time do I still have? Okay. So now we can actually study the Uru state to understand some property of the in state. And one thing in particular that so yesterday I asked 2 questions, right? Beside the one that we will answer in the second lecture about the problematic of thermal state here. One question was the fact that we had a finite flux of energy on Scray plus, and this flux was going on forever. And so observably on Scray plus will meet a constant flux and in an infinite times. Okay, the total flux is infinite, but also the time is infinite, right? But an observer, then we trace back all these modes. And we see that these modes pile up at the horizon. And the observer free falling, will meet exactly the same infinite amount of radiation, but in a finite and actually very, very short amount of proper time. More, yeah, a fine parameter if it's a null observer. And I asked, so is this observer going to see some divergence here, an infinite flux of energy, be completely destroyed by this infinite radiation? Because this is what seems that should happen, looking at here. But we also see that, okay, no, the stress energy tensor is exactly the same in the Uru state, which is fine at the horizon. So what is going on? Well, let's see. So this term here, this constant kappa over 48 pi, this is the term which comes from the radiation. Right? The fact that we have a particle emission at infinity is this term. And this term at the horizon is actually giving you something which is infinite, an infinite effect, an infinite amount of energy, because this is constant at the horizon, non-zero constant at the horizon. And once you go to the Kruskal coordinates, this is something which is divergent, right? But this divergence is exactly cancelled by the divergence that was there in the Boulevard state, which is just something geometrical. There with when there is no radiation. So you do see an infinite flux of energy. Well, I mean, there is an infinite flux of energy, but this infinite flux of energy is exactly the one that you need to cancel the infinite energy that you will see without it. Right? So what an observer actually sees is nothing special. I mean, it's crazy if you think about it. I mean, it's a very surprising result. You have some radiation that pile up here. Is actually infinite, the one you will cross infinite time. But what you measure is nothing special because there is also another infinite that is coming just from a different contribution. And the two cancel each other. I mean, it's not a coincidence because the point is that everything is self-consistent. But I mean, it's self-consistent. When you see there's something self-consistent, but you just do a very small loop, okay, it's nice. But when you do, like, you compute something from one root and something from a very different root, and then at the end of the day, everything is self-consistent, it looks amazing, I think. Huh? Well, we didn't include back action yet. So we computed the stress energy tensor, but we didn't put into the. I mean, yeah, this is what you put into the back reaction. So it means that the back reaction is not going to be huge and infinite. And so, yeah. 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 And 2, 3 minutes. Okay, I will say something more on this at in the next after the coffee break. I will say something more. But now there was something else I wanted to say because the other question I asked was what about energy conservation, right? Because we had this flux of energy created out of nothing, and nothing can escape black hole. So if nothing can escape black hole, how can I even in principle make sense of energy conservation? I mean, this setup is not going to conserve energy because we are not considering a back reaction. But at least in principle, how will they do that? Right? And again, we can answer this question by looking at the Uru state because it's a simple state and it reduces to the state we are studying there at the horizon. And in particular, we can look at the flux of incoming energy, this TVV component. This TVV component gives some, shows what is the flux of incoming energy here. And if you do the computation, I mean, the computation, you just take TVV and you evaluated it at the horizon. So R equal to 2m. And remember, this was finite and it was fine because V is a good coordinate at the future horizon. So this means that everything is finite. So if you do that, you get okay again. Well, let me cancel something. Let me cancel here. You get in PVV in at R equal to 2 PM. What is it? This is minus 1 over just some number. Again, the number might be wrong, so check it. Or anyway, it's not relevant. But what is relevant? You have something which is negative flux. And if you instead compute it sorry, then now you compute the UU component. So the right going component at R going to infinity, which basically means on square plus. the number again might be wrong, but the point is the same number. And this is the end of the lecture. But before finishing the lecture, so this result that we obtained by looking at the stress energy tensor is telling us that the flux of energy you have at the horizon is negative, as Ramon was pointing out. So you have a negative energy entering into the horizon. Let's do it here because this was a space-time. So you have a negative energy entering into the horizon. And on Scrape Plus, you have exactly the same flux, but outgoing. And this is how, in principle, you could conserve the energy. I mean, we are not considering the back reaction, but this is how you could do that, because the mass of the black hole will shrink because we have this negative flux of energy going in, not because anything is going out, nothing can go out, but because you have negative energy going in, and this negative energy going in is exactly the same rate of the positive energy that you see at infinity. And this is how you can, at least in principle, conserve energy. But of course, that computation does not take this into account. So with that computation, what you will get is that in total you have infinite flux of energy inside the black hole of negative energy, and you have infinite flux of positive energy, and the mass of the black hole is constant even though you have an infinite energy going in. But this is just because we are ignoring the back reaction. Okay? So this is how the mass can decrease, not because anything is going out, but because negative stuff is going in. Okay. Apologies for the extra minute. Okay, do you have any questions? Otherwise, we can continue after the coffee break. I think it's difficult to interpret here because you cannot talk about particles near the horizon. You cannot talk. It's just have a negative flux of energy. In this sense, the interpretation that Atterbuck was mentioning before, that is heuristic interpretation given by Hawking, it is capturing something. Right? You do have positive and negative state. One split at the horizon, and one goes to infinity and one enters in. But this is a very heuristic picture. I will not take this too seriously. I just think that the stress energy tensor is something which is well defined, the expectation value, and there is something which is, Yeah, you had a question? Vacuum cleaner, vacuum. What does it mean?
This mentioned the amount of bit. Like, I don't know, get that.
Yeah, we can check the paper together later. Uh, mm, yeah, also when the mass goes to zero, right? Does it go to Yeah, yes, for sure, but it would be nice to have some meaning. Yeah. The temperature is yeah, it's outside the semi-classical limit, and then the temperature is divergent. Yes. As Luca mentioned, the end of Silvano, like the definitely it's outside the semi-classical limit, but one thing is being outside, one thing is whether the model should do something weird, right? Because the mathematics is consistent even for very small g, I don't think. But as Luca mentioned, that is the temperature goes to infinity. So this is
say at mass going to infinity,
Yeah.
we don't consider zero, but GM is fixed.
yes.
So it's definitely based on that. So you have like
No, but yeah, but what I was trying to say before, I didn't say it well, is that one thing is whether or not I trust the model in that regime, and one other thing is why the model is giving something weird in that regime, right? So there are two different questions. So I don't trust the model in that regime because what you said is beyond the semi-classical limit, but also the model gives something weird because the temperature goes to infinity, so you have divergence because you have infinite temperature. You have infinite temperature, so this gives you something which is very large.
There's also a short question on Zoom. Is this related to the Penrose process? Who does? Okay.
No, the Penrose yeah, is this related to the Penrose? So you mean the energy extraction from black holes? No, I will not say this is related. That is a completely classical process. This is something which truly quantum in nature. So
I forgot what interpretation to have some convergence of the horizon on the state. So the negative contribution of the horizon is also needed to give you something which is then
well, no, that's not related. So that is negative constant, but TVV must be finite at the horizon. So yeah, it could no.
Vacuum cleaner vacuum in particles are in quantum state.
Mhm.
There are
Yeah, of course. Yeah, you can define another different vacuum because we have defined something which is vacuum here but divergent here. So you can have something which is divergent here and define it here. Yeah. I mean, I didn't discuss that because it's less interesting. Yeah, but yeah, okay. Yeah, I didn't know it was this name. Yeah, but yeah. So it makes sense the name, right? Because it's deleting particles from the space time. Okay.